Welcome everybody to the fifth of our Frank Jackson Professor lectures on net zero. And I'm very excited about this one. You should be too, because it's likely to go horribly wrong. This is where we couple together the model we built in lectures 2 and 3 of how the temperature of the climate system responds to changing atmospheric concentrations of CO2 with the model of the carbon cycle, how carbon dioxide concentrations respond to emissions of CO2, to see what happens as you vary emissions. Because in the end, that's what we need to do to understand how the climate system responds to our emissions, both in the past and in the future. So there they all are, and they were working, and then they stopped working, and some of the audience members witnessed them stopping working, so we're hoping we've recovered. I should give a shout out in this lecture, of course, in addition to Ben Perry and Toby Rolls, who built this machine in the first place, I should give a shout out to Lily Freshen, who helped me couple the two together, and thanks to Lily, in between doing her doctorate on machine learning and climate science and rowing for the university. Yes, you should be really impressed by that. But okay, so I'm going to talk to you here about what was christened back in 2009 as the trillionth ton result, or the trillionth ton of carbon. But I'm going to start by going back a little bit before then to when the need for net zero first became clear to me. And this was a conference in 2005 held in Exeter at the newly established Hadley Centre for Climate Prediction and Research. The Met Office had recently been moved down from Bracknell to Exeter, and this was one of their sort of first big flagship international conferences. And it was convened by Tony Blair, remember him? And the two questions that the conference was posing were, for different levels of climate change, what are the key impacts? Because we want to avoid dangerous climate change. That was the name of the conference. And then what would such levels imply in terms of greenhouse gas stabilization concentrations and emission pathways to achieve such levels, such stabilization concentrations? And the sort of crucial point here is we were talking about stabilization concentrations and the emissions required to achieve them. And just shortly before, the conference was all planned out, you know, the international conferences are over several months before it actually happened. But just a few weeks before the conference happened, we'd published a paper in Nature, although which made quite a lot of noise at the time. It was the first widespread use for climate applications of distributed computing. So we handed out lots of different versions of a climate model to people's home computers, and they ran these model simulations for us, sent us back the results, and we plotted how much warming we would get. And what we found, disconcertingly, was that for models, I've shown you this top picture before in the second lecture, I think it was. But the really important result in this paper was actually the plot at the bottom, which shows basically how bad the model is. And you can see, so up is worse, so bigger error. And you can see there's lots of pretty bad models here, big errors. But then there's not much difference between these best models here and the ones out here, which warm by 10 to 12 degrees when you double carbon dioxide concentrations in those models. So we found by just running the model lots and lots of times and varying things we didn't know in the model, because these models contain what we call parameters, numbers which we set to make the model work, but which represent some physical process in the real climate. We don't really know what these parameter values are. And we varied these parameters in the model, and we got all sorts of responses out of them, and included a handful of models that gave us these very, very high responses. And that was, of course, so the scientific community was kind of interested in how we'd done it, the distributed computing angle. Metro, quite a young publication at the time, was excited about the fact that 11 degrees, that's how much hotter scientists believe that the world will get. Well, that wasn't what we said. What we said was it could get that hot eventually, given what we know only based on comparing climate models to observations. In other words, you could devise a model that wasn't that much worse than the best models we had at the time, not significantly worse, and which gave you masses of warming for a doubling of CO2 concentrations. The other big muddle was that we were predicted to reach doubled CO2 concentrations. Well, at the rate we're going, we depressingly still are, but hopefully we're changing the path a little bit at the moment. By maybe 2060, 2070, it would have taken a very long time to get out to these very high temperatures, and we'll explain why with our Gresham climate model in a minute. Of course, Metro sort of ignored that and just said, it's going to be 11 degrees by mid-century, because that made it a more exciting headline. And they weren't, I'm picking that out because, it was the most dramatic cover. What I really like about this is that having read this article about how we're all going to die, you can check out our great going out guide. So London hasn't changed very much. Going back to our presentation at the 2005 conference, here I found the old laptop, which actually I'd used at the conference at the time, and managed, to my surprise, to get it going again and get the presentation off it. So here's one of my slides, basically, so what should our Tony, so this whole conference was about questions Tony Blair was asking, and what I was saying, so what should our Tony have asked? And I was arguing then, not what level of greenhouse gases in the atmosphere is self-evidently too much, but what injection of greenhouse gases into the atmosphere is self-evidently too much. So it's a slightly different question. And the point I was making in my talk was that this second question was one we could answer objectively, based on things we could observe, that didn't depend on speculation about whether the world would warm by 6 or 10 degrees when you doubled carbon dioxide. And of course, it's interesting that looking back, I could have written this slide really last week. Apparently we don't like to talk about this because the answer makes people feel uncomfortable. Because, of course, the obvious implication is if we carry on burning carbon forever and dumping CO2 into the atmosphere, we will warm forever. The final point, and this I think we have made some progress on, I was asking why should we focus on the unanswerable question of what's the right stabilization concentration? So the big question of this conference, remember, was should we aim for 550 parts per million or 450 parts per million? That's concentration of CO2 in the atmosphere. Or even 350 parts per million. There was a whole movement at the time saying 350.org, we should go for 350. And the point was that was an unanswerable question, because we couldn't say when the warming would stop if we stabilized at a particular level. And later that year, from another talk, I found some conclusions here. Basically, summing up, the notion of a sustainable emission rate per head of population in the world of carbon dioxide is indefensible. We can't observe the things we need to observe to say what the right rate is. And that instead, we were trying to promote the idea of what we called a containment scenario at the time. I was thinking that's a slightly odd language, but I realized at the time, you may recall there was something else going on in 2005, and there was much talk about containment. It was Tony Blair's jargon for what we were trying to do in Iraq. It didn't really work very well, but it was so anyway. So we were talking about a containment scenario as analogous to that, hoping that the politicians would get it. Anyway, and the point, then we gave some numbers. With 500 billion tons of carbon released already, and then we said back then, in 2005, we could release another 600 to 700 billion tons of carbon, so that's a little bit more than the same again, before the risk of warming over 2 degrees exceeds 20%. And so that means if you extrapolate how much we emit from land use and how much we emit from fossil emissions, that means a total fossil carbon emissions of 1 trillion tons. So let's go forward 18 years and look at the latest estimates from the Global Carbon Project. Well, the budget they give for 2 degrees there is now expressed in, a few years after our paper, everybody decided that we're going to start using units of carbon dioxide rather than tons of carbon, which was annoying for everybody because you have to divide by 44 and multiply by 12 a lot. But it's just a unit conversion. So in the modern units of billions of tons of carbon dioxide, we're saying, 3,725 billion tons of CO2 is the budget for 2 degrees. Do the unit conversion, 1.02 trillion tons of carbon. So that makes us look awesome, okay? But I would like to point out to you, actually, we didn't do that well. Because what they're saying now is the best estimate for the total budget for ending up at 2 degrees. So that's 1 trillion tons of all emissions from both land use and fossil sources. We were saying back in 2005, we could probably get away with burning fossil fuels alone and getting up to 1 trillion tons. So we got the principles right, but we were over-optimistic on the numbers. And I should stress this was work I did with Dave Frame, a New Zealander. He's now a professor back in New Zealand. And I think in defense of our talk in 2005, we did get the principles right, but we didn't get the numbers quite right because we claimed there was a better chance of staying below 2 degrees if we burnt 1 trillion tons than we would say today. The problem was, it's interesting looking back, why did we get the numbers somewhat wrong? And the answer was we were using, back then, an over-optimistic carbon cycle model. And the reason we were using a pretty over-optimistic and rather crude carbon cycle model, it was the carbon cycle model, it wasn't our carbon cycle model, it was one due to Bill Nordhaus, the economist who got the Nobel Prize for a few years ago for his work on the economics of climate change. But he had written his own carbon cycle model, but when you ask an economist for a carbon cycle model, you may not get the most up-to-date one. And so we were using his because it was nice and simple. And neither of us knew anything about the carbon cycle. So we gave this talk. To be honest, it got a bit of a raspberry. There wasn't really, people were sort of like, okay, that was amusing. But now go back to your homework, which is working out what the right concentration of greenhouse gases we should be aiming for in the atmosphere. And we kind of reverted, and so we were rather discouraged, really, from the response to that talk. And we went back over the next couple of years, really, to our knitting, which was trying to work out what was the warming you would get when you doubled CO2 in the atmosphere, and we carried on failing to work that out, and so did everybody else. So, interestingly, that very same year, Pierre Friedlingstein and Susan Solomon, a very well-known, well, both of them very well-known atmospheric climate chemists. Pierre Friedlingstein is a specialist in the carbon cycle, knows all about the carbon cycle. Susan Solomon's an amazing atmospheric chemist, and she was one of the core people who discovered the mechanisms responsible for the ozone hole in Antarctica. And they did a very simple experiment with emissions over here going up over time, and then they just asked the question, what would happen if we just stopped emissions in each individual year? What would happen to concentrations in the middle panel, and what would happen to the temperature response? And so, unlike Dave and me, who, we did know something about the temperature side of the problem, so that was what we were quite good at. They knew lots about the carbon cycle side of the problem, so they got a realistic carbon cycle response. If you sort of remember the shape of these curves, and you'll see curves like those later when we come to talk about the carbon cycle. But what they found for the temperature was that when you zeroed emissions, they predicted that temperatures would actually carry on rising and then fall again. So they published their paper, but nobody really kind of got the implications. And they certainly didn't sort of ask questions about, so what happens as we just add up the total amount of CO2 in the atmosphere. So it's an interesting example of, you need to understand two disciplines to get the result. You need to know something about the carbon cycle, and you need to know something about the thermal climate system. And science, and this is particularly for students, science is full of silos, and we all work in our own narrow little discipline, and we get very good at that. And it gets very nerve-wracking when you're doing anything that involves somebody else's silo. So as soon as we, Dave and me, started talking about the carbon cycle, we got a pretty, not so much hostile, but more just rather poo-pooing response from carbon cycle modelers. There, you don't understand. The carbon cycle is very complicated. And it is very complicated. And carbon cycle models at the time were very complicated. But they, as we learned over the next few years, we had to learn carbon cycle science in order to connect these two things up. And, then everybody got distracted. Susan Solomon was the co-chair of Working Group 1 for the IPCC's 2007 fourth assessment report, so she was a very, very busy person indeed over the next couple of years. The Intergovernmental Panel on Climate Change then won a Nobel Prize, shared with the Nobel Peace Prize, shared with Al Gore. And I took a year out to look after Jim because my wife got a very responsible job just as Jim appeared on the way, and it was clear somebody had to go and look after him. So that sort of knocked me out of the arguments for a little while. I'm pleased to say Jim has turned out better than the IPCC's Nobel Peace Prize. Those of you may remember, there's a bit of a jinx in the Nobel Peace Prize, that things tend to go wrong after you're awarded it. And things went very badly wrong for the IPCC a couple of years later. But it set us back a few years, but we're sort of back now. But relevant papers did continue to appear, and one particular one, which I should highlight, although it didn't make much noise at the time, was led by Damon Matthews, a Canadian. The title says it all. Stabilizing climate requires near zero emissions. And they did a variant of Susan Solomon and Pierre Friedlingstein's experiment, but with a more sophisticated carbon cycle and temperature model. So they actually had both the temperature model and the carbon cycle model getting close to sort of more realistic. And they showed that if you ramped up cumulative carbon dioxide emissions, that's the top panel there, then a flat line corresponds to net zero emissions, because if you're not increasing, if you're not adding further emissions, that means you've reduced your emissions to zero. They got more or less flat temperatures. So this was the point of their paper, was that, and this was in late 2008, people were starting to sort of nibble around this result of the fact that, maybe actually, there might be a different way of thinking about this problem, of asking ourselves, what do we actually have to do to emissions to stop the warming, rather than talking always about stabilization concentrations. And finally, in 2009, things got very busy. And it's interesting how in science, again, people sort of skirt around a problem. Dave and I were quite shy about publishing that talk we gave in 2005, because, as I say, we got a bit of a raspberry from the carbon cycle modelers. And, it all seemed a bit too simple just to say, well, every ton of carbon we put in the atmosphere puts us up temperature by about the same amount, and that's the whole story. All these people who'd been doing all these really complicated things, to sort of, for two people who'd never done any carbon cycle modeling in their lives, to rock along and say, actually, it's really simple, was, we didn't have, I'd love to say we were brave enough to do it, but we weren't. We didn't publish the paper. But then these papers were coming up, and other people were talking about it, and we were giving talks. And that's the way science works. We were going to places, giving talks about this, getting feedback, getting comments, and crucially, getting co-authors, including Chris Huntingford, who was a carbon cycle modeler. And so we were able, in 2009, to join in a whole series of papers, which all sort of bubbled up at once, arising, many of them, from the conversations which have been going on over the past few years. Susan Solomon and Pierre Friedlingstein appeared again, irreversible climate change due to carbon dioxide emissions. Then, in one issue of Nature, we had two papers, one led by Malte Meinshausen. You'll notice Dave Frame and I are on that author list. The other led by myself and Dave Frame, with Malte Meinshausen on the author list. And this was one of these sort of coordinated publications where the two groups had kind of done the same thing. And Malta's a very nice guy. And the origin of this was that he was at the 2005 workshop and had just finished a new version of what was called the Magic climate model. It was a coupled climate carbon cycle model. And he was kind of looking for things to do with it. He'd spent a lot of time computing, sort of sorting the model out. And now he was wondering, what experiments should he do with his new toy? And I suggested to him, well, here's an interesting experiment. Why don't we just look at the impact of cumulative carbon dioxide emissions? So he took that away and went, and then when he started to get some interesting results, he came back and he said, here's some interesting results. And sure enough, Dave and I were doing exactly the same thing, but with a different model, the other side of the world. Malta was working in Australia, and we were getting much the same results. So cue lots of busyness and writing papers at very high speed, and we submitted them simultaneously to the journal. And it doesn't happen very often, but I'm sure journal editors are very nice. They're always nice, but on this particular occasion, the journal editor was nice enough to say, okay, fair enough. He could see that two groups had basically done the same thing, and it was legit to co-publish them together. So they both appeared in the same issue of the journal. And then Damon Matthews, who I mentioned before, he actually had a paper which was going through the process at exactly the same time. Again, he'd visited us in Oxford. He'd been involved in these conversations, and his paper came out just a couple of weeks later, talking more specifically about the proportionality of global warming to cumulative carbon emissions. And then a few months later, another paper came out led by Kirsten Zickfeldt, which had actually been submitted the year before. So it's again, working in parallel. Damon Matthews was also involved in that one, pointing out that quantifying what sort of emission targets we would need to limit the risk of dangerous climate change. And finally, very different format, a paper led by Jonathan Gregory, also featuring Pierre Friedlingstein, which was all of these papers are in the sort of the sort of nature science proceedings of the National Academy of Sciences journals, where you have sort of short, punchy papers which make headlines. Jonathan doesn't really bother with those kinds of papers. He wrote a nice long paper in Journal of Climate which explained it all and had lots of equations in it, and didn't cause nearly as much excitement in the press, but actually if you go back, it did, for the first time, introduce the phrase, rightly it's credited with introducing the phrase, the transient climate response to carbon emissions, the TCRE, which is the phrase we use these days to refer to this ratcheting effect of carbon dioxide. As you put a ton of carbon dioxide into the atmosphere, you drive up global temperatures by the same amount. So just to sum up, that was the sort of bit of history of it. This is the result with some figures from those papers from 2009. The big one here is from our paper, and in the horizontal, you've got cumulative emissions of carbon dioxide. That's the total amount of carbon dioxide we dump into the atmosphere over the entire industrial epoch. And in the vertical, the temperature you get to, that's where we are now, or where we were back then. Notice we were well below 1 degree back then. Anyway, that was the day. Anyway, and so we were predicting this increase, and the sort of complicated shading is showing different lines of evidence, all pointing to the same basic results. And Damon Matthews' paper, figure from Damon Matthews' paper, very similar results, different line of evidence, different scenario, but again, the same basic point that the more carbon you put in the atmosphere, the warmer it gets. And the modern range looks like this. And by the way, you'll notice there's various coloured symbols in our figure. These ones from Chris Huntingford, from various different models, show sort of more or less straight lines, which more or less align with the modern estimate of the range. The white symbols, which were from what I did, so sort of curve a bit. And so you could say, well, Chris kind of got it right, and I maybe was not quite right about that curvature. And we'll talk about where that curvature came from in a bit. But, we were pretty much in the ballpark, got the right range, as did Damon. And so that was the first result, which is the more carbon you put in the atmosphere, the warmer it gets. And the second result was that if you stop putting carbon in the atmosphere, you get little further warming or cooling. So the temperatures just stay at that level. And here's a couple of figures, one from Susan Solomon's paper, which basically showed this ramp up zero emissions, so this is concentrations here, and you can see she's using similar models to the ones she was using with Pierre Friedlingstein a few years earlier. Concentrations drop off and temperatures remain more or less constant after zero emissions. Kirsten Ziegfeld's paper, they did something really ingenious, actually. They did the whole problem backwards. They said, what about if we wanted to get to this temperature pathway, what would we have to do to the concentrations, and then what would the emissions be that would be allowed to give us those concentrations? So unlike the rest of us, we were all sort of putting emissions into models and seeing what happened. They said, okay, well, let's define what we want to happen and back out. And you can see that they reach the point that basically cumulative emissions go flat when temperatures go flat, which means net zero emissions. Although, again, this wasn't a very punchy conclusion. So probably the kind of figure that really summed it up for people, we put actually into, we sort of realized this figure was needed to explain these papers, and we actually pushed it into a little commentary that we published also at the same time as that, those coordinated publications in Nature, just to make the basic point that these three emission profiles of carbon dioxide have exactly the same area under the curve. The yellow is the same as the yellow, so the area under the blue curve is the same as the area under the orange curve, which is the same as the area under the green curve, so they all correspond to the same total amount of carbon dumped in the atmosphere, and they all give the same temperature outcome, and with tiny differences which are well within the uncertainty in the outcome, and you end up at the same place, and you end up with flat temperatures at the point where you get to net zero. So warming continues until carbon dioxide reaches net zero. So that was the result. And now we're going to talk about, I hope we're going to talk about understanding why this result happens using our Gresham coupled carbon cycle model. So remember, this on the right, on the right is the thermal system. So red is energy being pumped into the climate system. And if I initialize everything, there is a, sorry, okay, I miscued. Apologies. And it's probably easier to explain this if I just let this run through, and we'll start again. Okay. Apologies. Right. I will reset so that we can explain things properly. What I meant to happen was just to get this set up so that that is the climate system in equilibrium with energy coming in from the sun, going back out into space, and this is the background energy flow in the natural climate system before we mess around with greenhouse gas concentrations. And if you remember the oceans lecture, this is the surface temperature here, and this is the temperature of the deep oceans, and they're connected to each other. As we warm the surface, we also see warming of the deep oceans. Remember that sort of whole thing we went through So I will get rid of my CO2. If only we could do this in reality. And start again. Did I overdo it? No, I didn't. Great. Right. So now I'm going to do a scenario, I hope, in which we assume, basically the Rio 1992 scenario, the stabilization scenario, where we aim for a particular concentration of greenhouse gases in the atmosphere. And so watch what happens so just to sort of, we're going to bump up emissions, and then we're going to hold them constant for a certain amount of time. Okay, that's how we're going to start, and then we're going to see how everything responds. Right. So here we are, pumping CO2 into the atmosphere at a great rate. Immediately, it starts flowing through into the biosphere, which is also going up, and then gradually trickles off into the oceans. Now, this is a scenario where we're keeping concentrations constant in the atmosphere. So you can see the concentrations are staying stable here. We're still emitting, slower than we were, but we're allowing ourselves to carry on emitting because we're saying we want concentrations to stay stable. But look what's happening to temperature. The speed of this pump is proportional to the level of CO2 concentrations in the atmosphere. It's keeping on rising. Watch carefully. I hope it's not going to overflow. Okay, this is all you got to, yes, okay. Demonstration ended in time. Okay? So, did you notice the temperature carried on going up after? Okay, a few people nodded. I should have drawn your attention to that earlier, because that's the sort of fairly subtle point. But that's the point. If we stabilize concentrations in the atmosphere, the temperature keeps rising. And I should have emphasized this before, that the speed of this pump is linked to the depth of the fluid in this column, because that's the concentration of CO2 in the atmosphere. And that determines the extra energy that's being pumped into the climate system because of the elevated greenhouse gas concentrations. So that was the stabilization scenario. So now if I reset things, it takes a little bit of resetting, but bear with. I want to go back to our sort of pre-industrial climate. So we're back to 0. And we're going back to, the 19th century, so we haven't dumped any CO2 into the atmosphere yet. Okay. That's slightly too long. Okay. Right. So now we're going to try a different scenario. I didn't switch that off quite fast enough, so I'm just going to do one little correction to get it back to the same level it was before. I want to push the ocean temperature back up to its equilibrium. You see, it should have been up there. I didn't switch that fast enough, so we're just pushing it back up again. That's close enough. Okay, so we're back to where we were before, and we're now going to try another scenario. So we've got no emission, back in the 18th century, we haven't started, James Watt hasn't done his stuff, so we haven't started pumping CO2 into the atmosphere, and we've got this just natural flow of energy through the climate system. Right, now we're going to run a different scenario. To just remind you what happened in what we just did, stabilizing atmospheric concentrations allows emissions to continue for a very long time, many decades to centuries after the point you stabilize, and then temperatures keep rising. And you saw that happening in this. So now I'm going to try a different scenario. Watch carefully to both what happens to temperature in this column and what happens to CO2 concentrations here. So as that rises, the speed of that pump goes up and temperatures go up. CO2 concentrations are rising, temperatures are rising, but as soon as we stop emissions, they've now stopped entirely, the concentration of the atmosphere fall and the speed of that pump fell because that immediately reduced the energy, extra energy flow through the climate system. And watch what's happening to temperature. It's staying more or less constant. Even though concentrations are actually coming down steadily in the atmosphere because we are leaking carbon out into the deep ocean. So it's a very dynamic system. We've got all sorts, before the whole experiment stopped, we had concentrations falling in the atmosphere, we had concentrations rising in the deep ocean, we had temperature rising in the deep ocean, and as a result of all these things going on, the temperature at the surface stayed constant. So that's net zero. It's not an equilibrium static situation. It's a delicate balance between lots of things that are still going on after we stop emissions that happen to give us no further warming or cooling of the surface of our planet. So here we are. One I prepared earlier, as they say. Stabilizing temperatures requires declining atmospheric concentrations of greenhouse gas, of carbon dioxide, which requires net zero carbon dioxide emissions. And we can go one stage further, if you'll bear with me, and let me just reset this one more time, because I'll just reset us to pre-industrial conditions. Right, so we're back to where we started. So now we'll do a different experiment where we put in the same total amount of emissions, but over a longer period. Okay? So, watch what happens. We've got more or less the same starting conditions. Off we go. See, pump's not quite as noisy, but it's going on for longer. Okay? Watch what happens to temperature now. It's going up slower, but it's still going up, and concentrations are going up to not quite the level they went to before, but do you remember where the temperature went to before? It's gone to the same level. So that's the other big result, is that it doesn't matter whether you go up and down like that, or whether you go up and down like that. It's the area under the curve that matters, that determines your final temperature. And the peak concentrations are actually rather different. If we compare this figure to that one, you see peak concentrations are actually much higher in that case, where we pumped it in really quickly. But the temperature we end up at is much the same. And as a final experiment, bear with, okay, which is to show you what happens when we to get the sort of last element of the result. Which is, so here we are, same temperature for the same cumulative amount of CO2, even if it goes in at a different rate. And finally, we're going to try a scenario, the peak concentrations are very different. We're going to try a scenario in which we just go in half the rate, but for the same amount of time as we did to start with. So we're putting in half the amount of emissions. Remember where it went before, went to there, the temperature. Here we go again. So now it's going at half the speed. But it's only going in for the 11 seconds or so we did to start with. You can see concentrations don't go up as high. And do you see where it got to? Pretty much half where it got to before. So that's the proportionality between the total amount of carbon dioxide we dump in the atmosphere and the warming we get. And you won't see this behavior, that combination of net zero warming or cooling after net zero emissions, and that proportionality between the amount of carbon we dump in the atmosphere and the temperature we get to, unless you have this level of complexity in your coupled climate carbon cycle system. This is as simple as it can be to give you that essential result. So if you sort of resent the number of pipes I'm showing you, that's the way it is. You can't get rid of any of these pipes. There's no aspect of this that is redundant if you're going to understand those two big results. The fact that you get proportionality between carbon dioxide, total carbon dioxide that we dump in the atmosphere and the warming we get, and that that after emissions reach net zero, we get no further warming or cooling. So it's all sort of reducing this to its bare essentials. And I should stress to you, the equations the sort of simplest set of equations that we can solve to simulate this, what we did in 2009 was all quite substantially more complicated than this. And I've spent a lot of the subsequent years actually working out what was really needed then. Did we need that complexity? How can we strip this down to the simplest possible system to really understand the essentials of what's necessary to understand versus what's incidental? And this is it. And on that note, we shall stop our demo. But it's gone well. Right, half the cumulative, there's half the warming. Okay. There's one complication that I didn't work out how to represent with fluid and pipes, which is that if you remember in lecture 2, I emphasized that there was a curve between the amount of carbon dioxide in the atmosphere and the warming you get, identified by Svante Arrhenius many, many years ago. And that's this curve here, which shows as CO2 concentrations in the atmosphere go up, the rate at which the CO2-induced warming goes up, it continues to go up, but it goes up a bit slower over time. And fortunately for us and for the success of this demo, there's another complication, which is that as you pump CO2 into the atmosphere, more of it stays there. So this curves upwards. So this is the total amount of carbon dioxide we dump in the atmosphere in the horizontal here, and the total concentration of CO2, or total amount of CO2 in the atmosphere in the vertical, and you can see that curves upwards. So if it was a straight line here, that would correspond to just half the CO2 we dump in the atmosphere remaining there every year. But what actually happens is that bends upwards because as the world warms, more and more of the CO2 we dump in the atmosphere stays there, because the systems, the biosphere, the oceans get less and less good at mopping up our carbon. Then we've got this curvature in the relationship between CO2 concentrations and warming, and those two curves cancel out by, in my view, a bit of a coincidence, although there's others who take a stronger view that there's something deep here. I don't think it's anything particularly deep. I think it's just a bit of a coincidence. They cancel out and give us a nice straight line, which is convenient because it means there is a very simple relationship between the total amount of carbon you dump in the atmosphere and the warming you end up at. And this sums it up from the Intergovernmental Panel on Climate Change report, the fifth assessment now, led by Thomas Stocker, which highlighted this result, and it was great credit to Thomas, actually, that he spotted that this result mattered and made sure that it was elevated in the IPCC report and really put in front of governments and said, look, you need to understand this. And this is a plot from that report which shows the total amount of carbon you dump in the atmosphere and the warming you get for a number of different scenarios. And they're all lying in this plume of uncertainty, just like the other figures I showed you. There's a simple relationship between where you put what you put in. It doesn't matter which scenario you choose, whether you put it in fast or slow, you end up with the same amount of warming. And why this particularly mattered was, at the time we were publishing these papers, we dumped about 500 billion tons of fossil carbon into the atmosphere. In the 15 years since then, we've dumped another sixth of a trillion tons of carbon. So we've gone from 500 billion to 2/3 of a trillion tons of carbon in 15 years. The first 500 billion took us 250 years. That gives you a sense of how fast we're, rushing towards this. If we go on up to 1 trillion tons of carbon or 3.7 trillion tons of CO2, that's what would be enough to take us to 2 degrees. I produced this graphic back when 2 degrees was kind of what we were aiming for. And of course, if we wanted to go for 1.5 degrees, we'd have to shift that graphic to the left, and we'd have less carbon to dump in the atmosphere. So just as we've chewed up the remaining carbon budget by carrying on dumping CO2 into the atmosphere, we've also moved the goalposts forward in that we've decided actually we don't really like the prospect of going to 2 degrees. And in Paris in 2015, we agreed to aim for 1.5 degrees, making it even more urgent that we stop dumping CO2 into the atmosphere. And the crux of Malte Meinshausen's paper in particular, and I should really credit Malte for drawing my attention to this, because I didn't really know anything about fossil fuel companies and fossil carbon reserves and all that sort of thing. But he pointed out, this was in 2008 when he visited Oxford, and he said, look, the reason this really matters is that proven reserves on the books of fossil fuel companies are out to sort of well over 2 trillion tons of carbon. So that's aggregate coal, oil, and natural gas that we know is there, we know is economic, certainly economic at today's prices, which, if we just sort of let things happen, is going to get burnt and is going to end up in the atmosphere. And if we include what they call resources, which are potential reserves of carbon, which are just sort of haven't been proven onto their books, might not be economic at today's prices, you can take it out as far as you like. There's plenty of fossil carbon down there. And this is why it matters, and this is why it really mattered that this result was taken up with lightning speed by the policy community. And I know people like to snipe at the slow pace of climate policy, but it is amazing that these papers were published in 2009. It definitely helped a whole bunch of papers coming from different groups, all reaching the same conclusion. They were channeled into the Intergovernmental Panel on Climate Change report, published in 2013, and were acknowledged, and the reality of net zero was acknowledged in the Paris Agreement only 2 years later, in 2015. And we'll talk about the implications of that and how we got there to the Paris Agreement in the next and final lecture of this series. Thank you.
I've got a couple of questions from online before going to the room. The first one is, how much of the trillion tons that we've already burned do you think, how much of the trillion tons have we already burned, and do you think we will avoid burning the trillionth ton?
Sure. So in units of carbon, when we published the papers, we just burned the first 500 billion tons. We've now burned about 2/3 of a trillion tons, so in the remaining, in that 15 years. And remember, 1 trillion tons of carbon is what takes us to 2 degrees. So if we want to limit it to 1.5 degrees, we really need to limit the injection of CO2 to 3/4 of a trillion tons of carbon. So we're at 2/3, and that's uncomfortably close to 3/4. So we're running out of road. Do I think we'll avoid burning the trillionth ton? I don't, but there's a very important element which, if you go back and look at those slides from my 2005 talk, was another thing I didn't know about at the time. There's an alternative to burning and dumping into the atmosphere. You can burn and put it somewhere else. So I think we will burn the trillionth ton because we're kind of addicted to using fossil carbon, but there is an alternative. We don't have to dump it in the atmosphere. So I'm hopeful that we won't emit it to the atmosphere, although whether we'll stop emissions to the atmosphere in time to limit warming to 1.5 degrees, I'm much less optimistic, because we really are running out of road on that one.
The second question I've got here is, does the straight line relationship between warming and CO2 emissions imply the need for net zero?
Yeah, I mean, this is a question that comes up a lot, sort of when sort of explaining this to students and so on. It doesn't really, even if it was curved the way we supposed it would, you could still have that result that you need net zero emissions. It'd be a different configuration of pipes would give you that. No, they are. I think they're two separate results. The fact that you've got this balance between all these things going on after you get to net zero emissions, with atmospheric concentrations coming down just fast enough to slow down the pump, to slow down the flow of energy into the climate system fast enough to halt the warming at the surface, compensated for by that warming continuing in the deep ocean. That's one set of balances. And then the other set of balances, which is the sort of proportionality between cumulative carbon emissions, which sort of the balance between that upward curvature of the carbon cycle response and the downward curvature of the temperature response. I think they're separate results.
I've got one more question from online before going to the room. How safe will carbon storage be, and what are the dangers?
Well, safer than putting it in the atmosphere. But yes, I mean, that's one of the big challenges we have over the next 20 years, is to establish safe ways of getting rid of CO2, because we're going to have to get rid of CO2 on a colossal scale. And we'll talk about the implications of that in the next lecture.
Are there any questions from the audience in the room?
Thank you very much. Thank you very much, Professor Myles. Notwithstanding whether or not we can put that extra carbon back into storage, do we not nevertheless have a moral obligation to reduce our carbon emissions, particularly at a personal level, and given the climate injustice between rich and poor? I know you're a philosopher by training.
Yeah, no, absolutely, and we most of that first $500 billion came from countries like this one. Most of the current $500 billion is actually coming from other countries that are developing fast and have every right to develop. And yes, I think there are very important justice questions in terms of, how those that have grown rich on the back of fossil carbon, and Britain is a prime example of that. I mean, the reason London is the wealthy city it is, people, slavery had something to do with it, but burning fossil carbon had a lot to do with it. We, Britain, got the fossil carbon habit before anybody else did, pretty much, and that's how Britain got to be so wealthy. So, yes, I think we do have an obligation to stop earlier, and also to develop the technologies that the rest of the world will need if they're going to use their fossil carbon as they propose to without causing climate change. I think there's another responsibility there that we have, which I think we in particular have a responsibility to develop and demonstrate to the world safe disposal of CO2, because we've generated so much of it in the past. Whether or not we rely on it for ourselves, we can probably stop generating CO2 in the UK almost entirely. We're a post-industrial economy. We don't really need to generate fossil CO2 anymore. Certainly not on the scale, not on the scale we do. But other parts of the world are in a very different position, and so I think we've got an obligation to them to develop that technology so that they can then make the choice about whether to burn their fossil carbon or not.
Not just what we create in this country, it's our consumption.
Yeah, absolutely. And we are buying stuff from, so it's wrong to blame other countries for generating carbon dioxide, making goods that we want to buy from them. I mean, they're doing it for us, so to speak. And so there's a lot of, we will be talking about these in the final lecture.
So how has the response of governments to this trillionth carbon data point changed between 2005 and 2015? Has there been have they accepted it more, or have they discussed it more, or has it been the same?
Well, we really nailed down the numbers in 2009. So all of those papers came up with pretty much the same number that, trillion ton, total amount of carbon for 2 degrees, trillion tons, 1.5 degrees, 3/4 trillion tons. And that's remained the estimate ever since. So we're kind of, and that's, in many ways, that reflects the thing Dave and I got right in our 2005 paper, which was that if you ask that question, you keep getting the same answer. And that's a good thing, because the problem with the what's the right level question is, people say, oh, it's 550 parts per million, oh, it's 350 parts per million, oh, it's 450. It just wasn't getting anywhere. Whereas as soon as we start asking this question, what's the right amount, everybody got the same answer, and we kept getting the same answer. So that's tremendously helpful. On the sort of what's happened since then, well, we've narrowed the range of uncertainty in this. We understand much better than we did back then about what other things are doing. I've only talked about carbon dioxide here, and there's other very important drivers of climate change as well, and they add to the warming from carbon dioxide. So we've really advanced our understanding of that. But one of the beauties of this result really was that it was so simple, there was very little to add to it. Every ton of carbon you dump in the atmosphere ratchets up global temperatures by a little bit under 0.5 trillionth of a degree.
Yeah, so just with the version where you dump all the CO2 in and then we go net zero, and so the levels in the atmosphere start coming down and that manages to perfectly balance the temperature going up, is that also just a coincidence, or?
Thanks, that's a great question, and we're still arguing about that. Yes, is my answer. There are others who feel more strongly that it's something more fundamental. I mean, in a sense, part of it is fundamental, and it's the same ocean that's absorbing the carbon that's also responding to the temperature. So, there's a sort of similar time scale in there. But there's also the whole response of the biosphere, which is really complicated. There's the response of atmospheric feedback. You remember in lecture 2, I think it was, we talked about how when you warmed the world, the pattern of warming changed over time. I mean, there's no reason for that to be related to the long-term response of the carbon cycle. So I think it's a bit of a fortunate coincidence. But it's convenient. And actually, if you're interested, we published a paper on precisely this just recently, actually looking at what it's also a coincidence, and it's also an approximation, in that we showed in a paper we published quite recently that it's about zero, but you can come up with scenarios in which it's a little bit above zero, a little bit below zero. But we didn't make too much of a song and dance about that because we didn't want everybody to go away and say, let's spend the next 20 years working out exactly whether it's zero, because it's exactly what some policy folks might like to do. After all, that is what they did with the sensitivity question. They said, we don't have the sensitivity, so let's just not do anything. So it's close enough to zero. So, for practical purposes, it's zero. But there is still some uncertainty about exactly what that long-term residual carbon dioxide emission rate will be.
Thank you. My question is around carbon capture, because it seems to me like that's the grand conclusion here. And the impression that I get is that within the private sector, within conversations around ESG and the environment, offsetting and carbon capture seems like a bit of a option of last resort. And it seems like it's viewed in the private sector as less, the perception is that it's kind of cheating. And my question is, given that it seems like the inevitable conclusion is that we have to focus more on carbon capture, why do you think that is, and what can we do about that?
Well, I think a lot of people are quite confused, and we're going to talk about this in the final lecture, about what carbon capture needs to involve. It's not, people talk about carbon capture, and I don't blame you for this because everybody says this, they forget it's carbon capture and storage, permanent storage. And the point is, capturing a ton of carbon by planting a tree is relatively cheap. Capturing a ton of carbon and getting rid of it forever, which is what you have to do, is actually really expensive. And so it really is the last resort. It's generally much cheaper to reduce emissions than it is to dispose of the carbon dioxide you generate permanently back underground. So there's a sort of practical reason why the private sector regards it as the last resort, because it's expensive. And there's also the sort of philosophical reason that it's generally better to avoid generating waste in the first place than it is to struggle with coming up with ways of getting rid of it. But we are going to talk about this in the final lecture, if you don't mind me pointing forward to that, because that's a big question.
So before we say thank you very much to Professor Allen, can I just draw your attention to 2 lectures? There's a lecture tomorrow, what is the role of nuclear power in a net zero system? I think we're sold out for in-person, but if you want to catch it online, you should be able to log in for that. And then Professor Allen's next lecture is going to be How the World Agreed on Net Zero, 6 p.m, Tuesday the 23rd of May. Please sign up. Thank you so much, Professor Allen.
Thank you.